Thank you for all of you for coming again. This is the second session in our four-part course, which is being hosted by the Faraday Institute of Science and Religion at Cambridge and funded by the John Templeton Foundation. For those of you who couldn't make it to the first session, I'm William Simpson, a junior research fellow at Cambridge and the organizer of this online course, and I shall be chairing this session. Before I introduce you to today's speaker, I'd like to look back briefly over some of the ground we covered in the previous session. The fundamental question we're thinking about is, what is the world like and how do we fit into it? We want a general account of reality, which can incorporate what the sciences are telling us about nature, and which can also make sense of the possibility of human beings having such knowledge. It's no good giving a scientific story about reality which writes human beings out of the picture. Their ability to think about theories, act on ideas, perform experiments, scientific knowledge would not be possible in such a world. In the early modern synthesis put forward by philosophers like René Descartes, which we considered in the last session, science was supposed to explain the behavior of things in nature in terms of the intrinsic properties of their underlying matter and of universal laws, whilst human persons were conceived as immaterial entities which interact with but are irreducible to their material bodies. Brian Pitts of the University of Lincoln talked to us about both the coherence and tenability of Cartesian dualism today, focusing on the famous mind-body interaction objection against dualism. One form of this objection that Brian discussed is the energy conservation objection. To put it crudely, modern physics tells us that energy is always conserved, but mind-body dualism implies that it isn't. So much the worse for mind-body dualism. What Brian argued for, however, is the conditionality of conservation, which calls for a little more precision. Conservation laws, we learned, are tied to mathematical symmetries. Anything which makes a difference to how the physical stuff in a system behaves, in the sense of breaking the time symmetry of whatever physical laws are deemed to apply to that physical stuff, will violate energy conservation because it will break the time symmetry of these laws. But time symmetry only holds given the absence of any external influence on a physical system, and establishing the absence of such influences is an empirical question. According to Brian, pitting conditional conservational laws against substance dualism without first establishing their antecedents is begging the question. Those seeking to make a case against mind-body dualism might do better to look to neuroscience. Brian also talked to us about some complications which arise from Einstein's theory of general relativity, which he pointed out has an inbuilt tendency to resist the introduction of external influences, providing some independent reason for objecting to dualism. Brian suggested that this is more of an engineering difficulty for dualism than a conceptual problem with the idea. If God exists, he would set things up so that mind-body interaction would work. If you're an atheist nowadays, you're unlikely to believe in souls anyway. In today's lecture, Michael Esfeld, a professor of philosophy of science at the University of Lausanne, who has published widely in the philosophy of science, the philosophy of physics, and the philosophy of mind, is going to argue for a weaker form of dualism in which nature consists solely of matter points, which are nothing over and above the distance relations in which they stand, and persons are mind points, which exist within a normative network of rights and obligations. Whereas Brian focused on the physics of space and time to fine-tune his philosophical views on how minds interact with matter, Michael will be focusing on quantum mechanics to motivate a sparse conception of nature, which he calls superhumanism, and to underscore a categorical difference between matter and persons. I've enjoyed getting to know Michael's work and spent a chunk of my doctoral thesis arguing that he is wrong, but don't let me prejudice you. Quantum mechanics, as you will see, is a game changer in the metaphysics of science, and an ontology of matter points stripped of any intrinsic physical properties is an interesting way of solving a problem that philosophers have in making sense of quantum phenomena. But I'll let Michael explain that. Yeah, over to you, Michael.
Thank you very much, William. And as you mentioned, we are after the big philosophical questions here. And This is, of course, difficult to treat in 45 minutes. So what I shall try to do is to start from quantum entanglement, which Schrödinger described as the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. Go into Bell's theorem and quantum non-locality. So that will be the first part, and I apologize for the physicists among you. I will be rather quick on the physics, because we then want to go on to the metaphysics, namely a metaphysics of science that, as William mentioned, consists only of meta points and distance relations, and how we get from there to the mind, or how we get to an argument for a form of dualism there which acknowledges both mind points and meta points. Okay, so let's start from quantum entanglement, which is a formal property of quantum systems, in the sense that they are described by a wave function, and the wave function follows Schrödinger's equation, and the wave function is situated on a mathematical space configuration space, such that each point of that space represents a possible configuration of matter and physical point in physical space. And if you have just one wave function, then that wave function usually is entangled in the sense that it describes the evolution of the entire configuration independently of what the spatial distance of these systems is, such that you can then get non-local correlations. For instance, in this experiment here, which is done in Geneva, and you see here the Lake Geneva, and you see Lausanne. Lausanne is over there, and I'm situated now, localized somewhere here in the west of Lausanne, where the university is. And in Geneva, they do these experiments. So this is the group of Nicolas Gisin. So they have a source here, and then they send two quantum particles in the photons in this experiment in two opposite directions. They fix here a value to measure on them. So it's a spin in a certain direction. So for photons, depolarization, and then you get an outcome here and an outcome over there. And these outcomes turn out to be correlated. And now they may very well be correlated, but the decisive point is that they are correlated in such a way that what happens here in Geneva cannot be conceived as the common cause of their correlation. So what happens here is not already even in a deterministic theory fixed by what is here. And this gets us into how entanglement leads to non-locality, and into something that has been proven by Bell in his famous theorem. So let's switch now, turn this in such a picture here. So we have our two physicists, Alice and Bob, and Alice and Bob receive a measurement outcome. So Alice can be in this experiment here situated in Satigny, and Bob in Jussy, and there's a distance of 18 kilometers between both of them, such that their measurement outcomes are separated by a space-like distance. And that is to say that no signal that Alice can send to Bob or Bob to Alice can be such that it can influence each other's outcome if the signal does not travel with a speed higher than the speed of light. And to get an outcome, of course, you have to measure something. So the little a and b here signify the choice of the variables to be measured. So the angle under which the spin is measured. And then we have the past of the system, and lambda ranges over the past of the system. Now, this is taken from Bell himself, but I would have preferred the graphic to be such that lambda is only the past light counts. Here you could think of increasing the speed of light, and then you could have causal influences here. But the decisive point is that A and B are separated in a space-like way. And now, if you're in relativistic physics, so if Einstein's local field theory holds, then you would say that events that are separated from one another by a space-like distance cannot influence each other. And more formally, this gets us to the Bell locality condition, which is also known as factorizability for probabilities. So you have here the conditional probability for Alice getting a certain measurement outcome, and that outcome will depend on the variable that she measures, of course, the question that she asks, and the state of the system, the past state of the system, signified here by lambda. But if you add information about Bob's variable that he measured and Bob's outcome, that should not change the probability for Alice. Okay, so you could imagine that if we were in class now, and if you had the unfortunate fate to do an exam on this course, okay, and if some other course were going on, and then someone mentioned before something going on in Hong Kong. So if another course were going on in Hong Kong, but all the students at some time in the past, they were together in Cambridge, and the course in Hong Kong, let it be on ethics and meta-ethics, so some different topic. Then, of course, the result of the students doing the exam in Cambridge would depend on the examiner's question and their preparation in the past when they all were together in Cambridge. But whatever questions the examiner in Hong Kong asks and whatever answers the students in Hong Kong give would have no influence on the questions and answers asked in Cambridge. And if this were so, if it turned out to be that depending on what questions are asked in Hong Kong, the students in Cambridge fail or don't fail, and if they have failed the exam and they've happened in some sort of systematic way, you could sue us. So you could, and you would gain the case in court that someone somehow conspired or manipulated the exam. Okay, so if we are normal life, Bell's locality condition, Einstein's locality hold. No one, I mean, we would be very astonished that if something happening far away in space would influence what happens here. But in quantum mechanics, this is so. Okay, in quantum mechanics, this does not hold, this locality condition. The probabilities do not factorize. Given the information about the value, the variable Bob measures and Bob's outcome, the probabilities for Alice's outcome are changed. And Bell proved, it's the Bell theorem, Bell proved by means of certain inequalities that there's no theory possible that is in accord with the empirical predictions of quantum mechanics and that satisfies this locality condition. So this is what entanglement signifies. Entanglement is some formal property of wave functions that are used to describe physical systems and quantum mechanics. And these wave functions have this formal property because there's something funny going on in nature, namely that the dynamics, the laws according to which the development of the configuration of matter unfolds in nature are not local, whatever they may be. But a local condition, the locality condition does not hold. Now, as any theorem, you need more than one premise. So there's a second premise in Bell theorem, which is sometimes called free choice. But what it says is only that the choice of the variables to be measured by Alice and Bob has to be independent of the past state of the system. And this is a premise that applies to any experiment and also to any exam. So if the examiner knows what the students prepared when they come to the exam would not be valid because the questions the examiner asks must be uninfluenced by the past state, by the preparation state of the students. Otherwise, you could easily fail or let pass all your students. So this applies to, again, to any experiment that you need this independence, which is sometimes called free choice. We will come back to that later. And a further point that Bell makes is you prove these inequalities are formulated in terms of spin variables, and you measure photon polarizations in these experiments. But at the end of the day, this comes down to position measurements. And even if you're an instrumentalist, then you just look at the pointer positions as the outcomes as registered by your macroscopic instruments, and you would get the same results. So the readings of the macroscopic instruments or computer screens or whatever it may be are then such that they are influenced by one another at a space-like distance. And if you are more a realist-minded person, then the same holds again. So what you really measure in spin, etc., is how a quantum object is deflected by in this magnetic field. So whether it goes upwards, spin upwards, or downwards, etc. So Bell makes the point that all you have to pay attention here, and this will become important also in a minute, are the positions, be it of macroscopic instruments, be it the positions of microphysical objects. Now we have a puzzle here, and we have a puzzle in the sense that I guess most of us will share a locality intuition. We have Einstein's relativity theory, special and general relativity. So Brian talked on Monday on general relativity. These theories satisfy the locality principle. They are even construed such that they satisfy the locality principle. And in the case of general relativity, offer as a theory of gravitation without action as a distance, as a Newtonian mechanics. So just in brackets, some sort of non-locality was there in Newtonian mechanics, but it is a milder sort because gravitation goes down as with the square of the distance between the systems. So still you have a sort of non-locality in classical Newtonian mechanics, but it depends on the distance between the systems. And here the correlations are completely independent of the spatial or spatial-temporal distance between these two events. So Alice could be on Mars and Bob on Venus, and you would get the same results. And it is selective, so you need the past interaction of the system. So you cannot just influence any system in that way, but only particular systems that have interacted in the past so that their wave function is untangled. So that is pretty much something new, and that pretty much justifies the quote from Schrödinger, who said that as I had on the first slide, this requires just look back at it, that enforces its entire departure from classical lines of thought. Now, this is a very strong statement, because entire departure would suggest that we have to throw away all classical physics, and that would be a bad thing then, because then we would be lost. So the question is, what exactly do we have to throw away from classical physics, and what don't we have to throw away so that we can gain an understanding here? I mean, if you were to construct from scratch a completely new view of nature of physics, that would be hard work, and there's something seems to be right about classical physics. And of course, there's a whole debate about what is called the interpretation of quantum mechanics, which is not so much interpretation as different formalisms offered to come to terms with the condition posed here that locality fails. And Bell had a favorite, since we don't have, I mean, this is not about quantum mechanics, but we should move on. So I would just like to focus on Bell's solution, which is quite interesting, and that Bell says that there's no need to change our view of objects. So the objects can be the same as in classical mechanics, with some provisos to which we'll come in a minute. There can be particles localized at points in physical space. If they are thus localized, we avoid the measurement problem, because there's no puzzle as to how an object can be at some particular place when it is measured, because if they always have a definite position, then they are always somewhere. And a cat, for instance, always is an either of configuration of a live cat or configuration of a dead cat. So remove some of the other puzzles from quantum mechanics that are not directly concerned with non-locality immediately to focus on what is the real puzzle. So there's no problem in sticking to objects as in classical mechanics. And by the way, in brackets, there's no problem either, as I would say, but it would be much more controversial and it's not the topic of this afternoon for quantum field theory either. The name is somehow a misnomer, because also quantum field theory at the end of the day is about particles, I would contend. And at least formally, I mean, there are papers that show how this can be done. So please don't say that quantum field theory shows that all this is wrong. It does not show, although it would require more argument than we have time for now. What changes is the law, okay? Because before we had local laws, as in Einstein's physics, we had laws, non-local laws in Newtonian physics, but going down with depending on the distance of the objects. And so what changes in comparison to classical mechanics are not the physical objects, but the law of their temporal development. And this means that entanglement doesn't concern the ontology, or does not concern the ontology in the first place, but only the dynamics. And on the basis of this reasoning, we then get to one particular formulation of quantum mechanics, which is the one going back to de Broglie and Bohm, but which was put in a much more simple form by Bell himself. So in this theory, we have particles, as mentioned, that always have a definite position in space. So they are localized, they are individuals, they have a velocity, they have a trajectory. So nothing of this goes. And we have a specific law called the guiding equation for their temporal development. And this, you can imagine this as a nomological machine that takes as input the particle positions and gives you as output their velocity by means of the wave function. So the wave function, which develops according to the Schrödinger equation and always develops according to the Schrödinger equation, is some sort of a means here then to get from particle positions to the development of these positions in terms of particle velocities. And what is remarkable about this law now is that you have to take as input the whole particle configuration. Strictly speaking, it would have to be the particle configuration of the entire universe, but in cases like when you consider concrete cases like the entanglement here, two particles, you have to take the wave function of these two particles. Or if you take cases like the double slit, you have to consider the wave function, including the experimental setup, so whether one slit is open or two slits are open, etc. And this is how the non-locality is implemented here. The non-locality consists in positions developing in a correlated manner. And these are, and William mentioned in the introduction that at some stage he parts company from me, which is fair enough, but I think it is not yet at this stage. So there are a number of arguments, again, not for this afternoon, why Bohmian mechanics is a serious, or arguably the best, I would say, formulation of quantum mechanics, because it avoids, as we see here, this Einstein problem that there's somehow a spooky action at a distance, that somehow something somehow travels with superluminal speed or whatever it may be from here to here, or as instantaneously here and here. No, there's nothing of the sort here in the account of non-locality. What we have is that the positions of the particles, and there were also the positions of the macroscopic measurement devices develop in a correlated way. And the drawback, of course, is that there is no answer to the questions why they do so. So there's no answer to the questions why positions develop in a correlated manner. But then I would contend no one has an answer to that question. Now, some people may think that attributing a power or a disposition to the configuration of matter in general may help us here. So I guess William and I would part company here, and that is, and I concede that this is a serious issue, but at the end of the day, I would stand to the statement that it does not give us a further explanation of non-locality. In any case, for the time being, the advantage here is that we have an account of non-locality in terms of positions developing in a correlated manner without any physical entity traveling from one being at several places at a time, or traveling with arbitrarily high speed or instantaneously from here to there. And we get a solution to the measurement problem because, as I mentioned, particles always are in a definite configuration, so there's no puzzle as to how something can be at a definite place when it is measured. Then we have, and we can deduce, I mean, we from this dynamics, from this deterministic law of motion, with a further assumption that the probabilities of quantum mechanics and the status of probability is exactly the same as in statistical mechanics. They come in out of ignorance of the exact initial particle positions. Now, the interesting thing for the metaphysics is that quantum mechanics forces us to consider naked particles. I would say, and I would go as far as saying this is not a change in ontology with respect to classical mechanics, because also in classical mechanics you can conceive of mass and charge just as dynamical variables that tell you something about how particles move and not as intrinsic properties. But then in quantum mechanics, it becomes clear that you cannot consider that you cannot attribute intrinsic properties to the particles. You would get in all sorts of trouble if you try to attribute to them more properties than just positions. And if they just have positions, they are naked particles, so to speak. There's nothing, there are no intrinsic properties to them, no intrinsic powers. If you thought of intrinsic dispositions for each particle individually, you would get into very much trouble with an infinite number of dispositions, etc. That would be a very bad idea. You can do this on relational space. This has been shown as well. So you don't have to subscribe to a substantial, substantival background space or space-time. So you can do a Leibnizian Bohmian mechanics, and it accommodates presentism in the sense that you have here the particle configuration at one time. That's all that exists, and the law gives you if it's evolution. So you can do this in a presentist manner, and that may be important for free will, because some people, and for the mind as well, because at least the presentist theory that admits presentism and that admits things being definite at a point of time without having to exist and without their past or future having to exist is at least helpful for free will. And it gets us, so if we focus on this point, it drives home that things only have relative positions. It gets us to a metaphysics of science that has been developed for quantum physics, and that is called ontic structural realism. And the idea there is that properties don't have intrinsic properties, they are individuated by relations. And here, of course, if it is position, what individuates them is the distance relation. So we jump now, we make now a jump, but the jump is not big, from the physics with arguments for which I cannot spell out this afternoon, for Bohmian mechanics being a good candidate to make sense of quantum physics, to the metaphysics. Because if we take this seriously, we get to a sparse ontology of the natural world that I've called superhumanism for reasons that will become clear in a minute, and that stipulates two axioms only, namely that there are distance relations. These relations individuate simple objects, matter points, and the matter points are permanent and the distances between them change. So we have one type of natural relations, the distance relations. They are natural relations. They are world-making relations, because only things that stand in a distance to each other are in the same world. If you think that other possible worlds exist, it makes no sense to ask the question how far apart they are. But if something exists in the same world as you, then it makes sense to ask the question how far away that thing is. So we have distance relations, individuating matter points, and we have change. And I would go Leibnizian here and saying that change is as such directed, because we need the distinction between variation in a configuration, as on this slide. Here we have a universe with how many? With 1, 2, 3, 4, 5, 6 matter points, and they are individuated by the distance relations, in the sense that all there is to that point is that it stands in the distance to that point that is smaller than the distance it stands to that point, etc. And the distance it stands to that point, maybe 3 times the distance it stands to that point, etc. So you have relative distances, but they are sufficient to individuate the objects. So you get variation within the configuration, and then you have change of the configuration. It goes from being that configuration to that configuration to that configuration. And the little tau here is to indicate that the change is directed, but that it is not taking place in an external time, but you get time out of change. So all this is Leibnizian, and all this is to be meant as a parsimonious ontology of the natural world. And in the sense that these two axioms are minimally sufficient for an ontology of the natural world that is coherent and empirically adequate, that is to say, that can accommodate all of our physics. And I called this position superhumanism because it takes something from David Lewis' Humean metaphysics, which was mentioned already in the introduction to this course, which is, as David Lewis famously said, the doctrine that all there is to the world is a vast mosaic of local matters of fact, just one little thing than another. We have a geometry, a system of external relations of spatial distance between points, maybe points of space-time itself, points at bits of matter, or fields, maybe both. It's points of matter and the geometry. The distance relations are individuating them. And then Lewis goes on to say that at those points we have local qualities, perfectly natural intrinsic properties, which need nothing bigger than a point at which to be instantiated. We have an arrangement of quality, and that is all. And what I do is I cut off this last sentences, which is in blue here. It just gets Lewis into trouble, because these intrinsic qualities cannot be known. We have no access to them. And these intrinsic qualities, because we have it cannot be known, have no access to them, they make no difference. They are superfluous. Now, the usual reply would then be to say, well, he has some Humean reservations there, and that he thinks that they have to be qualities and categorical, let them be powers. Fair enough. But if they are powers, if you have in the power, individual powers of point-like objects, then you get into great trouble with quantum entanglement and accounting for the non-local correlations. These powers would have to be infinitely many, and that's not a good way to go either. And so the name superhumanism is just explained by cutting something off from Humean metaphysics, which is thought to be parsimonious, and then superhumanism is even more parsimonious. And it's being parsimonious That's the point now to which we should get. We should get to the mind. It's being parsimonious enables us to come up with an answer to the question how there can be free will in the physical world. So as Brian Pitts explained on Mondays, the conserved quantities objection is a non-starter. This objection does not go through. But still, we have the problem highlighted, for instance, in Van Inwagen's consequence argument that some of you may know, that laws and initial conditions seem to predetermine everything. So let the laws be deterministic. Perhaps they are probabilistic, but that does not change anything, because then they would predetermine objective probabilities for what you do. Let them be deterministic. That's the harder case. And as Bohmian mechanics shows, you can even have a deterministic quantum mechanics. So you will have to come to terms with the fact that the laws of nature may very well be deterministic. Then if you have the laws and if you have initial conditions fed into the laws, so if you have the initial conditions at an arbitrary point of time, let that point of time be the beginning of the universe or the Big Bang or something like that in the remote past. So if you have the initial conditions and the laws, then these entail all the propositions describing what happens in the universe. So it seems that at the initial state of the universe, far back in the past, it was already determined what you'll have for dinner tonight, and all your future is already determined. Okay, and that would be a bad thing. Humanism offers you a way out, because of this argument, because Humanism says that first comes the particle motion and then come the laws. According to Humean supervenience, the laws supervene on the entire mosaic, so the laws are fixed only at the end of the world. And some people have reservations. There are many problems or many reservations that one may have with that, and one may wonder whether this Humean view of laws as supervening fits well with scientific realism. And in any case, the laws are not what it is issue when it comes to free will, because the laws define what we can do and what we cannot do. So the laws allow me to choose for dinner between, say, cheese and fish, and but they don't allow me to jump to the ceiling of the this ceiling is not high, so I may jump to this ceiling, but if I wanted to jump over the next house out there, that would not be possible. So this does not hinder my free will, that I cannot jump over a building, etc. So the law issue seems to be irrelevant here, and at best irrelevant, and at worst it gets us into trouble with scientific realism. Now comes in superhumanism. On superhumanism, we only have positions in the ontology. And this means that all the dynamical parameters supervene on or are fixed by how the trajectories of the particles unfold. So if you apply this to classical mechanics, some particles are electrons. Why? Because they move in a certain way, namely electron-wise, so to speak. And because they move in a certain way, their movement makes true the proposition that they are electrons and have a negative charge. But they are not sitting there at the beginning of the universe with a negative charge. That is their intrinsic property. We removed all the intrinsic properties. I would go as far as saying that we can remove them, and we better remove them already for purely philosophical reasons, metaphysical reasons. But fortunately, quantum mechanics comes in here and shows that we have to remove that we cannot, that intrinsic properties are a non-starter. You would not get anywhere and coming to terms with quantum entanglement if you thought of particles having intrinsic properties. So what do we do then with variables such as mass, charge? They are all in the quantum wave function. What do we do with the quantum wave function? It supervenes. So the particle configuration having a certain wave function is a matter of its motion. So first comes the particle motion, and then comes the wave function. It does not sit there at the beginning of the universe. And there are good arguments that would show if you had an ontology of both particles and the wave function, that would be superfluous. Then you can be an Everettian that only has the wave function. So the wave function is a dynamical parameter that supervenes. So what superunionism does here, it applies the union idea for the laws to the dynamical parameters that enter into the initial conditions over and above the positions. So for superunionism as grounded in quantum mechanics, what the wave function of the universe is, what the values of dynamical variables are, comes out of the particle motion. And this now implies that the future particle motion of persons' bodies enters into the fixing of the initial values. The decisive issue is to reject intrinsic properties of matter. This allows you to have particle positions in the past that are fixed. Of course, you cannot change the past. There's no retrocausation or anything like that. But positions alone, of course, are not sufficient to make this argument work that laws and initial conditions predetermine everything, because for initial conditions, you need dynamical variables over and above particle positions. And these variables depend on what actually happens in the universe. So the future particle motion, including the motion of persons' bodies, enters into the fixing of the initial values of the dynamical parameters. This is just what follows from the ontology, which is the best ontology to fit quantum mechanics. So quantum mechanics helps you out with free will in the sense that even if the conserved quantities objection does not apply, which is completely correct, it does not apply, you can also deal with van Inwagen's consequent argument and the objection from there being deterministic laws out there, such that laws and initial conditions predetermine everything. Yes, the mistake is in thinking that there are initial dynamical parameters over and above the positions sitting, literally speaking, in the particles. So the unionism about laws is not decisive here. So if you're a realist about laws, fine. A cosmic power, to my mind, also is an open option. The discussion would then have to be whether it does any explanatory, whether it serves any additional explanatory purposes. So what we see here is that those people who think that into Bell's theorem enters a free choice premise, and that this gives us somehow free will, and they are on the wrong track, because the premise is only about independence of variables. And free will does not depend on probabilities in quantum mechanics, because you can have a deterministic quantum theory. All these arguments are non-starters. They lead you nowhere. The decisive point is that quantum mechanics gives support to an ontology which admits only particle position, that quantum mechanics definitely removes the idea of there being intrinsic properties or powers of individual objects, and that enables you to solve the problem of how free will can intervene in nature, because there are only particle positions in nature. There are not additional dynamical variables. These come out, literally speaking, of the particle motion, so that their initial values depend on the future particle motion, which in turn can be influenced by your free will. And free will is, the argument for free will is not anything about quantum mechanics in particular. Again, it is something about it's being presupposed for the very formulation, justification, and experimental confirmation of scientific theories. So why do you have free will? Because you're a person, because you're a reasonable being. You think of what you ask your question, what should I think, given sense data, what should I think, given biological needs and desires, what should I do? And now my Kantianism comes in, so the Kantian argument, which is also spelled out by Sellers, then 20th century American philosopher, and in his Myth of the Given, is that whatever is given to the mind of a person, this cannot determine the thoughts and actions of the person, because the person has to take the attitude, has to position itself to what, with respect to what is given to our mind, and endorsing it as a reason for thought or action. So this is then is, to my mind, the central argument for dualism, namely that the conception of any scientific theory, and also the conception of any thought, any action, presupposes persons as ontologically primitive, because it presupposes that person endorse something as a reason for a thought or an action. And if this were reduced to anything else, it would no longer be a weighing of reasons, because because you have to accept something as a reason. So suppose a physicalist says that all there is matter and motion, but a matter and motion in the world that cannot impose the theory that everything is matter and motion on us, because that theory is accepted, if it is accepted by somebody, by their weighing of reasons, and that weighing of reasons cannot be imposed from the outside, because then we would not have reasons in the first place. So there's freedom in thought and action, because persons turn something into a reason for belief and actions, and this also distinguishes free will from chance events, in which there's no question of reasons. So we get, so to my mind, at least this is the important or decisive argument for dualism, that any scientific theory presupposes persons as weighing reasons, or turning something or endorsing something as a reason, and are thereby ontologically primitive. And now the ontology of physics that I've employed gives you a guideline for how to think about minds. I have no objections to endorsing sufficient physical conditions for coming into being of minds and persons. So I personally have no argument for Cartesian dualism, but there may be arguments. So I would go with the physicalist and saying, okay, of course, brains and bodies and whatever it may be are sufficient physical conditions for something, for a person to come into being, but there are then no sufficient physical conditions for what they think and do. This does not supervene on pain of falling back into the pitfall sketched out before, that something would then have to be, as a physical matter of fact, being imposed as a reason on a person from the outside, which would imply that this is not a reason. Now, the interesting thing that we have here is that now the tools that we developed before as the tools for thinking about physics can be applied to the mind. So you can think, so minds can be thought of as mind points, because obviously they are not extended, and they are individuated by relations. So in the case of meta points, or something is a meta point because it is individuated by distance relations, and something is a mind point because it is individuated by normative relations of what some person should think or do, of what they are obliged or committed to thinking and doing what they are entitled to be thinking and doing, and what they are not entitled to thinking and being. So it is their normative status and normative web of rights, obligations, entitlements, precluded entitlements that defines a mind. Of course, this again is a Kantian stance that sees it considers normativity to be the central element about thought and action, and thereby distinguishing it from matter and motion. But in any case, so my concern this afternoon was about the physics. So the physics gives us an argument for parsimonious, the quantum physics in particular, gives us an argument for parsimonious ontology of meta points individuated by distance relations, and all there is to these meta points are the relations in which they stand. This enables us to make sense of quantum mechanics, and then we have to add a non-local law of motion for them, but we have to accept meta points as ontologically primitive in this case. We have a further argument which is not tied to quantum mechanics, but which holds for all science, which is the argument that any conception of a theory or of any thought that you think requires you employing concepts, which require you following rules, which require you answering the question, what should I think? So that this thinking and acting is not reducible to physics, so that we get to matter and persons both being ontologically primitive. And because the ontology of matter only is matter points and distance relations, there's no problem about how persons in virtue of their free will can make their bodies move in certain directions. We get a categorical, so that is perhaps a distinction, the second distinction. So I don't need substances. These persons can come into beings, may have certain a physical basis. We get to a categorical difference between matter and persons, and defined by the relations, the normative relations individuating persons come into existence only when there are beings that adopt the attitude to themselves and to each other of asking what they should think and what they should what they should do, and this is only accessible from within participating in the practices. This determine this web. So this is the sort of neo-Kantian dualism in contrast to Cartesian dualism, which to my mind does more than what is sufficient to accommodate minds. And I would say at the end of the day in philosophy, it's always the issue of overall coherence, and the sense of which overall view captures all the ingredients that we want to have and does justice to all the ingredients. So we are committed to science. I mean, if we are interested in science, we are committed to scientific realism in the sense that science is coherent and true as far as the account of the matters of fact that are in the world are concerned. But science is not all there is. Science presupposes persons that do the science, that formulate the scientific theories, and this implies, again, the commitment to persons as ontologically primitive. And we have the metaphysical tools to conceptualize this in such a way that in both cases we have points, unextended points that are individuated by relations. So distance relations in the case of matter, and normative relations in the case of mind. So I've tried in I think a little more than 45 minutes to give you an outline and to touch upon a few of the arguments of this view. And I guess I should stop here and let you have a small break, and then I look forward to the discussion.